recognize the power of this from a physics point of view. And again, of what use of it? Don't know yet. If I'm doing high energy physics, which is what I did, if I have a particle that is cruising along and I need to somehow identify it, if I expose it, I can expose it to an electric field, or I can expose it to a magnetic field, or sometimes both. As a matter of fact, it alternates between exposures. But if I expose it to a magnetic field, so if I expose it to a magnetic field coming like this, if the particle curves this way, I know it's a positive charge. If it curves this way, I know it's a negative charge. Not only that, if I know the radius of curvature here, then, and the magnetic field I'm controlling, V I can calculate, because all I have to do is pick 2 points and figure out how long it took to get from one to the other. I can come up with a ratio here of charge to mass of the particle, and that greatly narrows down what type of particle it can be. So this is an incredibly powerful tool. Now, at this point, because we're dealing with, in the high energy physics, you're dealing with millions, if not billions, of particles. And so once they actually do the experiment and they smash protons or whatever they're going to be into its target, and you get a shower of particles coming out and a whole bunch of sensors clicking off of, hey, something passed by here. There's several months of just pure computer processing to actually analyze the data before any physicist actually gets a hold of it. Because when originally they started doing this, they had cloud chambers. They took dry ice, basically. They took superheated gas. And so superheated gas means that it is still a gas, but it is just a hair's breadth away from becoming a liquid. And if a particle goes through it, disturbs it, that's enough to cause, in essence, boiling to happen. And you get these bubbles in this trail. And so you can see where the particles are going. At that point, you didn't need the really fancy equipment in order to figure out what kind of particle it was. Matter of fact, you could build a cloud chamber. The former high school chemistry teacher built one a couple years ago. But now, as the particles come in, for my project specifically, you had protons shooting against a carbon target. Enough protons make contact, and you get this shower of particles coming out of it. Well, you hit a whole bunch of protons against it. You'll have a detector here, detector here, detector here, detector here. And what it's registering is, oh, something passed by here, here. We had all these different places where the detector says, oh, a particle just passed by. And so now you have to piece together of, this particle passed by here, but which one of these was it? So maybe that one. I seem to have missed that detector, but maybe it's this one right here. And so you have all these different points. Somebody described it as, you know that the snakes in the can? You open it up and the snakes come popping out. It's as if you walk into the room and somebody's already done it and the snakes are all over the floor, and you have to piece together in which order were the snakes stacked in the can. That's similar to what this is happening here. Questions here? All right. All right, so let's do a quick plug and chug. I have an electron with a velocity of 4 × 10⁶ meters per second. It It is going into a magnetic field, we'll make that I hat. It is going into a magnetic field of 5 Tesla K hat. The line is fun. I hat, J hat, K hat. What is the force on the electron? Well, what's the charge of an electron?
Negative 1.6 times 10 to the negative 19.
Units?
Coulombs.
Times velocity, so I have 4 times 10 to the 6th meters per second I hat, cross 5 Tesla K hat. We crank through that. And I hat, well, first off, let's do the vector piece. I hat cross K hat,
J hat.
or, no, that is right. Okay, yeah, I, J, K, I. Oh, K hat cross. I cross K. I cross K, I'm going to the left.
Negative J.
Negative J hat. So I got a negative J hat there, I got a negative right here, which will cancel out, so I'm left with J hat. Let's go ahead and stick in the intermediate step. I got negative J hat times negative, and then working out the math, what do you get?
I got 4 times 10 to the negative 12 J hat.
You got 4 times 10 to the negative 12?
I got 3.2.
That makes more sense. 4 times 5 is 20, times that will give you a 3.2.
Oh, yeah, I did 5 times 10 to the 6 for some reason. I must have put it
Alright,
in
so
wrong.
it's 3.2 times 10 to the negative 12?
Yeah.
Okay. And that would be Coulomb, Tesla, let's put it in slightly different order. Coulomb, meter, Teslas per second. And then finishing it up. Yeah. The negatives cancel out, I'm left with 3.2 times 10 to the negative 12. What units?
Newtons.
J hat. So as you can see, a Newton is a Coulomb, meter, Tesla per second. So we have a unit of time here. A unit of time would be a Coulomb, meter, Tesla per Newton. Just a little fun side note, fun with units. So if this electron is traveling at the speed of 400,000 meters a second, what's going to be the radius of the curve? I have erased it. So we had QVD is equal to mv squared over r. So r would be mv over qv. Mass of an electron, 9.11 times 10 to the negative 31st kilograms. One off memory on that one, so I wrote off right. My speed, 4 times 10 to the 6th. Q, 1.6 times 10 to the negative 19th coulombs, that's meters per second. And my magnetic field, 5 Tesla. No, something's off there. QVD is mv squared over r, the v cancels out. I'm looking for r pops up. No, that is right, never mind.
.555 times 10 to the negative 6
Units.
meters.
So this thing would be basically traveling in an arc with a radius of curvature of about 4.5 microns. In high energy experiments, that's a really low speed, so it's not actually high energy there. It's also a very large magnetic field. The biggest magnetic field I think that we've been able to produce is 27 Tesla. All right, questions? All right, I'll read your minds again. You're going, hey, this is great, but what about the lab? Didn't you say that we were gonna actually do something to explain the lab part? You're in luck. We're going to. We're gonna do something similar when we derive the other forms of the Biot-Savart law with this. What is velocity?
Displacement over time.
So I've got q dx dt cross b. Again, I can bring the t over, and so I got q over dt dx cross b. The notation's a little bit sloppy here, but we have a charge per unit time that is
Current.
now dx is a differential, and so the notation's a little bit off. But if we're talking about an object that we're basically talking about a current that's traveling in a straight line, that's just the length of the current. So I L cross B, where this is the length of wire with current I. Bathed by magnetic field B. And the direction, it's the direction of L is the direction of the current. Therefore, so, do a quick plug and chug. If I have a current of 3 amperes that is flowing through, I have, let's say I've got my magnetic field coming out of 3 Tesla. And I keep erasing it. Oh, there we go. We'll keep that. Okay, half. And this distance right here is, what do we make that? Oh, I got 3 and 3. Let's change one of those. Let's make the current 8 amperes. this, 4 meters. What is the force on the wire? Well, the force on the wire is 8 amperes times the length, which is 4 meters, in the direction of the current flow, I hat, cross 3 Tesla K hat. Ninety-six newtons, and then I cross K. I cross K. Negative G.
Is it always gonna be a square? Is length only the length of, like parallel to the current?
The length is the length of the wire that is inside. So if I had made that 4 meters and that's 3 meters this side, and I had the wire going this way, then L would be 5 meters long.
Okay.
Or 4 meters I hat plus 3 meters J hat.
So is this a specific condition that lets that be true, or is that true all the time?
That if my current is constant and my magnetic field is constant, then yeah, that's true.
And does the wire have to be straight?
Yes, because, so I guess it is specific. Because if L cross, well, let's see, if L's curving around like that, and G is coming out, so L cross B, L cross B, L cross B. The direction of the force would be changing if the line is not, if the wire is not straight. And so if you're looking at a net force, you'd have to take that into account.
Okay.
So we could do that like with calculus or something?
Yes. I wasn't planning to, but if the crowd's demanded.
I'm good.
So it is being forced downwards. Yeah, and this is great stuff. I don't think that it can get even better, but we still need to connect it to the lab. Because the lab, we had 2 wires. Or we had current pointed in opposite directions. So we gotta deal with that somehow. Well, we've already done a lot of the hard work. If I have a wire that's going down like, with current flowing down like this, what is the direction of the magnetic field out here because of the current? Right hand rule. If I have a current that's flowing down this way, I'm gonna call that I1.
Would be into the board.
Into the board. And over here?
Out of the board.
Yep. Somehow, tapping it more lightly somehow makes it less strong, but I need to put fewer dots. Farther away you get, the weaker the magnetic field goes. Now, I have a second wire with a current flowing up. So when I'm on the left side of this black wire, what is the direction of the magnetic field?
Out of the board.
And on the right side?
Into the board.
Yeah. You wanna do it once more with great confidence?
Into the board.
All right. So I have these 2 magnetic fields that are sort of overlapping where's the magnetic field, the total magnetic field gonna be the strongest?
Center, or in between them.
Okay. And it's weakened on the outside. So, like, sort of a consequence of all of this is that if you can set it up like this, where you got stronger magnetic field, weaker magnetic field, the force ultimately is going to be in the direction of the weaker magnetic field when you got the conflict like this. So these two wires will be forced outwards. So this is going to be forced to the right, and that's going to be forced to the left. All right, so we have the red wire is exposing the black wire to its red magnetic field. Well, if we think about that, so we're going to look at this a slightly different way. My magnetic field is coming out of the board. My current is going up. The direction of force on this wire, all right, so I'm going to do another right-hand rule because you can't have too many. Remember as a child, and you might still do it, the finger gun. Assuming all of you had used a finger gun at some point. Now we're going to make it more sophisticated because we're college now. The Sten gun. You've seen British Commandos with the gun which has the magazine sticking out to the side. If you don't, you need to watch more World War II films. Or not, I don't know. All right, so the Sten gun kind of looks like that. I got my finger, where the bullet would come out, is the direction of the positive charge flow. So I have current flowing up like that, so I point my finger in that direction, or opposite the negative charge flow. Magnetic field is rarely by a single dot or a single line. Magnetic field is sort of all sweeping, so the three fingers right here is the magnetic field. So my finger is pointing upwards, magnetic field is coming out. The red magnetic field is coming out. My thumb, the trigger, the thing that sets everything in motion, that force, and I know I'm stretching on the words here, but the thumb points in the direction of the force. So my current is up, magnetic field is out, force outwards. On this one over here, the red line, the current is flowing down, magnetic field is flowing out, the force is